Hi guys. So today's lecture is going to be talking about something more related to the algorithms side of this course called recursion. So we'll go ahead and step into the slides here. Some quick definitions. A recursive algorithm is an algorithm that is defined by repeating applications of the same algorithm on smaller problems. Essentially, it solves a problem by breaking that problem into smaller subproblems, solving those subproblems, and then combining the solutions of those subproblems into one singular solution. Another definition, the base case, is the point at which the algorithm stops splitting into smaller subproblems. You'll hear me sometimes call this the stopping condition. A method that calls itself or refers to itself is known as a recursive method. And so you'll see here an example. The method name is countdown, return type is void, and it takes an input parameter of type int called x. And if we look inside of the method, there's an if-else statement. If x is 0, then print 0. Else, print whatever the value of x is, and then here's what's strange, right? You call yourself. So the method call made here is countdown, but we supplied a new input, in this case x minus 1. And so how does this work? Well, so first you'll notice that same code, right, is here on the left, just so you can refer to it as we step through what's going on. And the right here is kind of the path that gets followed or I guess you could say the recursive path. And so starting from top and then going down to the bottom, we're going to say x is 5 to begin with. So we call countdown 5, and we jump into the code over here. X is 5. Is x, or 5, equal to 0? No. So we go into the else statement. We print the value of x, which is currently 5. So that's what this is right here. Oops. And then we call countdown x minus 1, where x is 5, so at 5 minus 1, which is 4. And what this means is we now go back and restart this method call with a new value of x, which is in this case now 4. So x is 4. Is x or 4 equal to 0? No. We fall into the else block. We print the value of x, which is now currently 4. And that's what this is right here. And then, after that, we call countdown x minus 1, which, since x is 4, is 4 minus 1, and 4 minus 1 is 3. And once again, we restart the method call. So we restart the countdown method call, but in this case, x is now equal to 3. And so we repeat this process until eventually we reach a point where x is equal to 1. And you'll notice, once x is equal to 1, we call countdown x, or 1, minus 1, which is countdown of 0. And so in that particular method call, x is equal to 0. Is x equal to 0? Yes. So we print 0. And what you'll notice here is that in this particular if statement, there's no recursive call. There's no countdown call. And so this is what is telling you that the recursion has ended. And now you can stop your recursive call. And so if we look at the result here, we have the end result is printing 5, 4, 3, 2, 1, and then if this would go away, 0. And we can actually show that in code. I have here, so you'll notice just the class main. I have my main method, which all it does is call countdown 5. And then this countdown code is exactly the same, minus the static here. It's not a big deal. It's exactly the same as what is on the slides. And so if x is equal to 0, we print 0, else print the value of x, and then make a recursive call to countdown where we supply an input of x minus 1. So let's go ahead and see if this does work as we think it does. Taking a hot second. There we go. And so yeah, there you go. It prints 5, 4, 3, 2, 1, and then 0. And then when we hit that 0, we're done in this particular case. You'll notice in later cases that just because we've hit the base case doesn't necessarily mean we're done. But we'll learn more about that in a second. So if we go back to the slides, to further understand recursion, we must understand what is going on in memory. And more specifically, we need to understand stack memory and the role it plays in your programs, and more specifically, the role it plays with recursion. And so I'm bringing back a slide from the memory lecture that I've done a few weeks ago. And if we look, right, the memory region we're going to concern ourselves with is the stack memory region. And if we look at what the stack memory region holds, it holds local, non-static variables that are scoped to methods. So basically, any variable, local variable, that gets declared within a method gets put onto the stack. So keep that in mind as we continue talking about these recursive methods. And so Zybox actually has a good, or has a few good examples of how this works. So here, you can see here we have a public class, memory region X, and this class creates a static variable called myStaticField of type int. And it has two methods. The first method is a method called myMethod, which creates a myLocal variable called of type int. And then a second method, which is just the main method. And the main method creates a myInt variable and a myInteger variable. So we're going to go ahead and, this is actually going to show all the different memory regions, which I do find particularly useful. So yeah, to begin, the code regions store program instructions. And so you look at the code memory here, and you'll see it looks rather odd. The add R1, number 1, R2. We're not going to worry about that right now. That's assembly code, and that's actually a course that you will be taking either next semester or the following semester. The myStaticField is a static field and is stored in the static memory region. And so yeah, we've actually previously talked about that, right? The static variables have their own region in memory, and so this public static int myStaticField gets stored in that static memory region. And you can see that the value here is 33. So we continue running. Method calls push local variables on the program stack. And so when the main, which remember main is a method, is called, the variables myInt and myInteger are added onto the stack. So myInt right here gets put onto the stack. And then myInteger is also put onto the stack. Now you might be wondering, I had previously talked about objects memory is actually put onto the heap. But this is actually not an object's memory. This is a reference to an object. And so this is a variable, my integer, and what it holds is actually an address. And so this variable is local to the main method, and so it is indeed put onto the stack. You'll see here that my int is set equal to 55, which is why you see 55 in the stack here. But my integer at this point in the execution is set equal to null, which is why you see a null. So if we continue running the next section, you'll see here, right, new allocates memory on the heap for an integer object and returns the address of the allocated memory, which is assigned to my integer. And so yeah, this is where the heap comes in play. The new object, or the new keyword, will allocate memory onto the heap. And what it does is it returns the address of where that memory is on the heap and assigns it to the reference type variable, my integer. And so you notice that's why the my integer that's on the stack holds a value of 9,400, which happens to be the address of where this integer object lives. Now if we continue on with the execution, they reset the my integer to null, and they call my method. My method has a variable called myLocal. It sets myLocal equal to 999 and then prints its value. So this brings up an interesting point. The stack, it can hold local variables from many methods. It's not specific to one singular method at a time. And that's what you've seen here. Now, you'll notice that there's a comment next to the my method call here. And it says stack grows, then shrinks. And what does that mean? Well, what it means is when you called the my method, it declared a variable called myLocal. That local non-static variable declaration put the myLocal onto the stack, hence the stack grows. It's increased in size. But what's interesting is when a method call finishes, so essentially after the system.out.println myLocal here, and this method call returns back into the main method, it's finished. And so what happens is any local variables that have been put onto the stack due to the my method call get removed from the stack. And so that's why you see here the myLocal 999 is grayed out. It means it's been removed from the stack in this particular example. And so yeah, you can read that down here. Calling my method grows the stack, pushing the method's local variables onto the stack, and those local variables are removed from the stack when the method returns. Notice the local variables associated with the main method still remain. That's because the main method hasn't finished yet. So we continue running the program. When main completes, main's local variables are removed from the stack. And so that's why you see they're now grayed out. So to look at another example, this is going to just somewhat reiterate the same thing. Here we have a class bit counter. It has a method, or two methods. One method is called count bits. It takes in an input parameter of innum, of type int, and declares two variables, countInt and binary string. And then we also have a main method that declares a variable called numbits, and also makes a method call to count bits. And so we'll go ahead and run this. The numbits variable, it started with the main method, right? The numbits variable gets put onto the stack, and it's waiting for a result from the countBits method call. So countBits gets called. And now this is an interesting point. Input parameters are considered, to methods, are considered local variables. They're scoped, that variable in num here is scoped to the count bits method. And so it does indeed also get put onto the stack. And so you have in num, which is put onto the stack. You'll see it has a value of 7, and that's because count bits was supplied an input of 7 here. Count int gets declared, but at this point in the execution it hasn't been assigned anything, which is why you see nothing in its spot on the stack. And then binary string gets declared, so it gets put onto the stack. And you'll notice here at this point in the execution, they create a string object that gets put onto the heap, and the address of that string object gets returned, which happens to be 9400. And yeah, that's what that's talking about at the bottom here. We'll go ahead and continue running it. So eventually count int returns, and notice, okay, so it did it pretty fast, but notice that all of the variables that were associated with the count bits method, so the count int, binary string, and innum, all got removed when count bits returned from its method call. And so that's why you'll notice the num bits now has a value of 3. That's because count bits returned 3. And when it did that, all the variables associated with the count bits method were removed from the stack. Now, of course, this is saying that there's other instructions here, so presumably main hasn't ended yet. But let's say main had ended, then also the num bits variable would also get removed from the stack. So go back to the lecture. Knowing what we know now about the stack, what is the infamous error stack overflow? Now, you may not have actually come across this error just yet, but I assure you at some point when you program long enough, you will most certainly come across this error. And so what is it referring to? Well, it refers to filling the stack memory region beyond its allocated capacity. So if you imagine, right, your stack memory region is not infinite. It can only hold a finite amount of memory. And so if you completely fill that memory, eventually you've run out and your program will crash because it won't know what to do. You'll essentially be bleeding into other areas of memory, and obviously that shouldn't be allowed. And so Zybooks, once again, has a good example of this. We go to the recursion chapter, and we look at the Stack Overflow section. We'll go ahead and run this. So you'll notice here again that there's two methods. There's a my function method and a main method that essentially calls my function. And what they're implying here is that my function actually doesn't have a base case. It's just going to continuously call itself forever. And so we'll watch this. You start with main, you put the my var variable associated with main onto the stack, you call my function. My function, the input parameter and the local function variable get put onto the stack, and they keep getting put onto the stack because my function gets called infinitely. And so since there's nothing stopping this recursive call, eventually you hit the end of the stack region. You'll notice that's why the loc var right here is red. You've surpassed the end of the stack region. And this would throw a stack overflow error and crash your program. And so yeah, you can read the comment here, deep recursion may cause stack overflow, causing a program to crash. If we go back to the slides. So moving away from this Stack Overflow issue, We're going to look at one of the more, a different way that recursion might be used. And so if we see this example here, this looks almost identical to the previous example. It's the countdown method. It checks if x is 0. If it is, it prints 0. But in this case, within the else block, I've swapped the print statement and the countdown call. So countdown is actually getting called first, and then the print statement is getting called. And so what will this print? It certainly is going to be different than what was previously printed. And so once again, right, the code on the left here is what's associated with the this new countdown method. And to the right here is kind of the chain, this recursion chain that gets called. So we'll start off with x is equal to 5. We make the method call countdown 5. So x is 5. Is x or 5 equal to 0? No. We go into the else statement and we make our recursive call to countdown x minus 1, but because of the nature of this recursive call, we're actually not going to just yet execute the print statement. First, we must finish this method call here. And so that's essentially what's happening here is, so x is equal to 5, 5 minus 1 is 4, so we're essentially calling countdown of 4. We restart the method call, so countdown with x is now equal to 4. Is x or 4 equal to 0? No. We go into the else statement, and once again, 4 minus 1 is 3, so we call countdown 3, and the print statement still has not yet executed. And so we restart the countdown, except for now x is 3. Is 3 equal to 0? No. So we call countdown, and we continue all the way down until eventually x becomes 1. So countdown of 1 minus 1 is countdown of 0. We restart the countdown method call. And now is x 0? Yes. We print 0. And now we've reached our base case. And here's what's interesting is while the previous version of this method ended here, this version of the method does not end. And the reason being is we still have all of those system.out.println methods, calls to finish executing. And the order is important. This countdown, or this system.out.println 0 finishes this version of the countdown call, which was made when x was equal to 1. Oops. Which was made when x is equal to 1, which means that the system.out.println that gets executed is when x is equal to 1, so 1 gets printed. And when this print statement finishes, it finishes this version of the countdown method call, which was called when x was equal to 2. And so you can kind of see the pattern here, right? The print statement for when x is equal to 1 gets called, finishing this countdown statement. And then the print statement for when x is equal to 2 is executed, finishing when this countdown statement. And then 3, and then 4, and then 5, and so on. And so the result you get is actually the opposite of the previous countdown version that we had, wherein it prints the results in the opposite order. So the result is 0, 1, 2, 3, 4, 5. And you can also imagine this in terms of the stack, right? The initial call put x onto the stack, where x is equal to 5, and then the second call to countdown put another x variable onto the stack, but in this case its value was equal to 4, and then another x variable onto the stack whose value is equal to 3, and so on and so forth until eventually you get to the point where x's value is 0. And then when that countdown method call finishes, that x is equal to 0 gets popped off the stack, and the next value to work with on the stack is when x is equal to 1. Hence, where learning the stack data structure comes into play. You still need to differentiate the difference between the stack data structure and the stack memory region. They are two different things. But the stack memory region does function similar to how the stack data structure is laid out. And so we can look at another example of code. You'll notice that this is extremely similar to the same example that we just went through, except for now we have two print statements essentially surrounding the cursive call here. And so what is printed if countdown 5 are called, and why is it printed that way? I'm actually going to leave that for you guys to do. Oh, and you know what? I forgot. I was going to show you the result of the previous one. So remember, we swapped places the countdown call here. And I'll go ahead and run this. And if we were correct, it should print 0, 1, 2, 3, 4, 5. And it does. 0, 1, 2, 3, 4, 5. Just to show you guys what Stack Overflow looks like, I'm going to get rid of the -1 here. And then go ahead and run this. And what you'll notice is, yeah, so you get a whole bunch of these main.countdown, but if I scroll to the top, here we go. Exception in thread main, java.lang.stackoverflow error. And so why did that happen? Well, x's value never changes. And so essentially, when I called countdown 5, is 5 equal to 0? No. I make another call to countdown 5. Restart the method call, is 5 equal to 0? No. Make another method call to countdown 5. And so on and so forth. And this will infinitely happen because x never decreases. And since our base case condition, or stopping condition, is based on x being 0, and x will never become 0, so therefore this becomes an infinite recursive call. And as we previously talked about, essentially this x variable fills up the entire stack memory region, causing a Stack Overflow error. I'm going to go back to the slides. So there are two steps required in creating your own recursive method. The first one is writing the base case, or the stopping condition. And every recursive call must have a case that returns a value without performing a recursive call. And that case is called the base case. A programmer may write that part of the method first and then test just to ensure that you do indeed reach the base case. And it's possible that there are multiple base cases. So you've seen in our example that our base case was when x was equal to 0, but you could also have a specific base case for when x is equal to 1 or when x is equal to 2, in which case you might have, a larger if, else if statements. Oops. And it does say that every recursive method must have a case that returns a value without performing a recursive call. In our case, we just printed a 0, and I guess what was returned there was just a void. The big idea is that there was no recursive call performed. Now the second step is to write the recursive case. The programmer then adds the recursive case to the method, which is where the recursive method will call itself. There may be multiple recursive cases. So in our case, we only had an else statement where the countdown method called itself. But there could be, once again, else ifs, where there are different conditions where you might call yourself with different inputs. So looking at the same example as we've kind of been looking at before with this countdown method, what's highlighted in yellow here, if x is equal to 0, system.out.println 0. So this is the base case, right? There's no recursive call here, so it's going to stop the recursion. Now what's highlighted in green here, this is the recursive case, and we can see that because the countdown method calls itself in this particular part of the code. So a common error is to not cover all possible base cases in a recursive method. In our case, it seemed pretty intuitive that eventually x would become 0, but in more complex cases it may not be as intuitive, and it's possible that your recursion may work in such a way that it skips over your base case and then therefore will recurse forever until eventually you hit a Stack Overflow error. Another common error is to write a recursive method that doesn't always reach a base case. And we actually saw that in that example on REPL that I did, where I got rid of the -1 in the recursive call. And that's what caused the Stack Overflow error. And that was because our recursive call never actually reached the base case. And both errors may lead to infinite recursion, causing your program to fail or crash, which causes Stack Overflow error. And so that's all I have for you guys for this lecture.